Hey everybody, it's Tony from Adafruit, and I wanted to do a stream on the Circuit Playground board, so the all-in-one kind of electronics learning kit that Adafruit has. And I wanted to do a little demo to play with the microphone. So I did a stream last week with Circuit Playground looking at some of the analog sensors. And if you look at the description when this is up on YouTube, I'll put links to the old videos and any of the websites and things that I look at on there. But I looked at some of the analog sensors, so things like the temperature sensor, the light sensor, where it's a very easy to read kind of analog sensor, and that the voltage or the value changes directly proportional to the temperature or the light changing, so that you can easily map that to maybe changing the color of pixels or something like that. And then I briefly looked at the microphone, and we kind of saw that reading sound from a microphone is not necessarily as easy as reading like light level or temperature from a thermistor. It's not a really easy kind of linear relationship because a sound wave is a sine wave, so it goes up and down, and so the intensity of that, like the volume level, isn't a direct kind of linear relationship where if it's louder then it's always higher. You need to look at things like the amplitude of the signal. And so in this stream I thought, let's play with making a demo of Circuit Playground that does like a VU meter or a volume meter that lights up LEDs proportional to the volume of sound that you hear. So if it's like really loud, then a lot of LEDs light up, and if it's really soft, then not many LEDs light up. And we actually had a project that's basically does this code already. It's what I would consider it a classic Adafruit project, kind of like the Firewalker sneakers, just very iconic. So this is the Amplify project, where it was a volume-controlled tie, a wearable, so like a tie you could wear that would light up more LEDs based on the volume of sound that it heard. So let's just kind of jump right into it. I'll show you real quickly the project. So if we jump to this main view, so right here I have Circuit Playground, and if you notice, it's lighting up a bunch of LEDs as I talk. So if I talk really loudly like this, you see a lot of LEDs light up like that. But if I talk really softly like this, then just a few LEDs light up. So it's pretty cool. This is what we'll end up building in this stream. And in the web browser here, I have a link to, or I'm showing the Amplify project. So this is a great project. If you haven't seen it, really cool. I consider it a classic Adafruit project, and that it's just something that you haven't really seen a lot of other people do. And so Adafruit did a really cool one here. This is Colin sporting the tie. And the way it works is basically the louder the volume. So the microphone is right here, kind of up at the top of the tie. And then the louder the volume, it lights up more and more pixels on the tie as it gets louder. So kind of like if you've used the stereo that has these little LED VU meters, same idea for this. So the cool thing is, so the code for this project, it was based on using I think a Flora board, the Flora, which is the same processor used in the Circuit Playground. So it's very easy to port this code over and make it work on Circuit Playground. And I'll show you how I did that. So if we go to the code for this, then we'll actually start looking at the code and digging into it. Now, if you do want to play with this code, I've actually committed the code that I'm going to build in the stream to the examples in the Circuit Playground library. So just like before, you want to set up your Circuit Playground so you can program it from the Arduino IDE. Make sure you can program like a basic blink LED sketch like this one. So, I'll press the upload here, and this is going to upload to my Circuit Playground board. And make sure that you can actually talk to the board before you dive in and start doing some of these examples. So you see this is doing the blink demo. It's just blinking the LED on number 13 every second. But if you install then in the sketch, include library, manage libraries. So go into the library manager and just search for circuit, and then you should see Adafruit Circuit Playground. And I just committed this example, but it's probably not in Arduino's package index just yet, so wait until like tomorrow and it should be there. But once you have this installed, then go into the examples and open up the Circuit Playground VU meter example. And so this is the code that we'll use for this example. And you can actually just upload this as is. So I'll just press the upload and we'll put it on the Circuit Playground board. And it should be all ready to go. It's there's nothing to configure for it. So you see it's running now, and as I'm talking, it's increasing LEDs. So the LEDs start down here with 0, and they wrap all the way around to this one. This is the 10th LED right there. So pretty cool, pretty easy to get started. And I'll show you what I did to make this work. So if we look at the code for Amplify, there are 2 sketches in here. There's one sketch at the top that's kind of set up to have like a fixed value. It doesn't really deal with like very soft or very loud signals. You kind of have to tell it ahead of time, this is the type of signal that I expect to see. And I was actually trying this one out, and it doesn't work super well because I think it needs a few things tweaked. So we can come back to this maybe and look more at like why this example doesn't work super well. But there's a second example here that's a little more adjustable, and this one works really well. So this is what I use to base the code off of this example that I'm running right here. So if I copy this code, let's just make a new sketch and start hacking on it. So let's do a new sketch, and let's just replace all the code with what I copied in from the Amplify project. Now, if you're following me along directly and you're actually copying this code out, one thing to be aware of is that it uses the NeoPixel library. It doesn't use our Circuit Playground library directly. So our Circuit Playground library we took all the libraries for all the components of Circuit Playground, like NeoPixels, the LIS 3DH accelerometer, and we put them all into one library so that you don't need to go and download a bunch of libraries. So it's a little bit of a convenience there. But if you're taking other code for other chips and processors, you might need to go and install some of these libraries. It depends on yourself. And remember, the easy way to install libraries is using the library manager. So manage libraries and just search for libraries and install them in Arduino. It's super easy these days to do that. So you load this up, and there's a little bit of configuration that you need to tweak at the start of it. So basically this n pixels, this is the number of pixels in your NeoPixel strand, because the Amplify project was kind of made to be generic, so you could use it with any strip of NeoPixels. For Circuit Playground, it's a fixed number, so we only have 10 pixels that you want to use. Now you could limit it, like if you only want to do half the pixels, so maybe this first half here, you could do like 5 pixels instead of 10 pixels, but I'm going to stick with the full 10 pixels. Now the mic pin, this is basically the input from the microphone. So Amplify is made to use with a little electret microphone that basically just outputs an analog signal, and you feed it into an analog input. Now on Circuit Playground, this is fixed. So you have to use A4. That's the analog input that's connected to the little microphone on the board. So there's a little microphone kind of right where my finger's pointed. And that's just connected to A4. You can't change that at all. Now you could, if you had another microphone, you could hook it up to one of the analog inputs that are on the outside of the board, and you could definitely read that if you wanted. So that's fine to do. And then the LED pin, this is the pin that's connected to the NeoPixel signal input. And if you look on the board, it's right here where my finger is. It says that number 17, and so that's for pixel number 0. So that's what we want to put here. And again, that's fixed. You can't really change it. Although you could hook up another strip of NeoPixels to like one of the outputs on the outside of the board, and you could power it that way if you wanted. So you're free to build it however you want. Now the rest of this you don't really need to change, but we can tweak some of these later. And I'll kind of walk through the code, and you'll see how this stuff works and why some of this stuff matters. But this changes, like there's a period of time where it'll take a few samples, and then it's going to look for the minimum and the maximum value within those samples. And then there's like a fall off period where you can see, like as I talk, so if I talk really loud, then you see the pixel kind of animates falling back down. And that's because it's taking your max value, and then it animates, like even as your sound stops, it'll animate that falling back down to 0. So it's kind of a neat little kind of animation to just show you, here was the max value that you saw for the sound volume. And then the input floor and ceiling, this is kind of giving it a hint as far as what range of values to get from the microphone. And so you can tweak this to increase the sensitivity or decrease the sensitivity. So if you give it a really big range, then the sensitivity is going to be less because it needs to hear a really loud volume level to go to light up all the way to the end pixel. Versus if you make this smaller range, like maybe if I cut this down to like 100 or 200, then just a very soft speaking voice would probably light it up to much more pixels here. So it's cool that you've got these little knobs you can tweak to play with these and kind of start to understand what does it mean when I change this range of values, and how does that relate to how loud of a volume that it hears. for this. So okay, so I tweaked those values. Now that should be it. I'm just gonna hit compile, and it's gonna want me to save this. We'll say play VU meter. And then, okay, and oh, so this is the other annoying thing. You might get this error here where it says F-scale was not declared in this scope. This is a weird bug I've noticed in the latest versions of Arduino where normally, so in the C and C++ language, when you have a function like this wheel function, it needs to be declared before any code calls it. And you know, normally you have like a header file that you put the declaration in. So the declaration is basically just this line right here that says, you know, what is this function? So there's a function called wheel. It returns a uint32 type. It takes in a byte as a parameter. And that's all you need to know to declare the function. And then to actually define the function, to give the code for it, is this full block right here where, you know, you have curly braces and then you've got a bunch of code inside of here. And basically, if other code wants to call this function, it has to be declared before that code calls it. So, you know, you need some line somewhere that says, you know, hey, here's my function, and if I go down here, you know, here's a declaration for this function. You have to put a semicolon at the end there. And then any code below this can call the wheel function, you know, like call like wheel 30 or whatever, and it's all good. Now, Arduino hides all of this from you though, because in theory, Arduino will actually go through and see what functions do you have in your sketch. So I've got like wheel, I've got this F-scale function, I've got the draw line, and then a loop and a setup function. And it will actually go up to the top of your sketch and it will automatically add in, you know, it'll basically just throw, here's the wheel declaration or definition, here's, you know, F-scale definition. For some reason though, and it's only in, I don't know, the last few versions of Arduino, I've noticed it doesn't, something is broken and it's not doing these definitions. So if you see an error like this where it says, you know, F-scale was not declared, and you go through your code and you realize like, oh, F-scale is a function, it probably means that something's a little weird and it didn't pick up this definition. So you can actually just manually define it yourself. So if I copy out the function definition, so just everything up to the curly brace, and I go up to the top of my sketch, and it doesn't really matter where I put this. I could put it, you know, at the very top up here. So we'll do that. Add the definition, and then don't forget to put the closing semicolon on it. And then if I hit compile, now it should work. And so we're just kind of doing what Arduino normally manually does or automatically does for you. We're just explicitly giving this definition of the function in here. So a little tip, it kind of trips you up sometimes, unfortunately, that it's there. So okay, so that compiles. Now let's hit the upload. And we'll push this to the board. And sometimes I'm on Mac OS X, it fails. If it fails, just hit upload again, and it should pick it up. There's all this USB stack changes. So okay, so just upload it, and hey, notice that it's working. So now this version you might notice is a little bit brighter, and that's because the version of the code in the Circuit Playground library, it sets the brightness down to a lower level just because you can see at full brightness, like this is pretty bright. But you can actually call, there's a set brightness function if you want to increase it. But because I'm just using the Amplify code as is, it's not using the Circuit Playground library, it doesn't do any of the brightness changes for it. And you might notice too, it's a little more sensitive. So like I'm talking at the same level right now, but now it's lighting up to almost the 5th pixel. And that's because I tweaked this input ceiling value. So in the example in the Circuit Playground library, I increased this to 500. So it's normally at 300. Well, let's see what happens. I'm going to increase it to 500 and let's re-upload the sketch. And we'll see what happens if it picks me up. You know, I'm just going to keep talking at the same level. And notice it's down a few pixels now. So it's not, you know, it was going all the way up to here sometimes. And now it's just the first 2 or 3 pixels that it's lighting up. So you can see we increase the range. And let's go all the way to the max. Let's do 1023. Like this is the maximum value of the analog to digital converter. So let's see what this does. This should probably drop my voice down to a very low level. Then I'm probably gonna have to like yell to get it to pick it up. So okay, so just upload it. So yeah, now you can see I'm down at like level 2 and 1 sometimes. And if I talk really loudly, then it goes all the way to the top there. So, and hopefully I didn't blow out everyone's speakers there. But that's kind of cool. So, you know, we increase it a lot, and let's go down. Let's decrease this to like 100, and let's see what this does. So this will probably, you know, in theory, we should see with my normal talking level it jumping all the way around to here or so. And yeah, you can see like it's, you know, if I talk normally, it's going up to almost above like LED 5 and 6, and sometimes it goes even higher than that. So that's pretty cool. It's, you know, just one little knob here that you can tweak to change the sensitivity. I'll put this back down at 500 here so that we get down to more of a normal level. But then let's kind of dive in, and I'll look at the code here, and we can see, how this works, like what it's actually doing to generate this signal that it's using to light up the neopixels. So if we look at the setup code, most of this is just kind of boilerplate stuff. So there's this commented out part that we want to leave commented out. Basically, for if you're using an external reference for the analog to digital converter, then you need to specify it here. For Circuit Playground, it's already set up. It's using 3.3 volts as the analog to digital converter reference, so we don't need to do anything here. And then it just initializes the neopixel strip, so it just turns them on and clears them all. Now in the actual loop, this is where it starts to get interesting. And so let's see, we'll maybe increase the sizes a little bit so you can see more. So let's just kind of go through this just like piece by piece to see what it's doing. So the first little bit here is just some housekeeping. It's declaring some variables that it's going to use. One important thing is that it's looking at like what's the current time. And so this is a really common thing when you're doing animations. You want to look at how much time elapsed since the last time the loop ran, so that if you're doing an animation, like you want to make LEDs move at a certain speed, you need to know how much time elapsed so that you can use the velocity to figure out how many LEDs to move around. So super common kind of convention or thing that you'll see in a lot of code. And then what we do is we basically do a loop here for a window of time. So we just say, okay, how many milliseconds do we want to sample the analog input? And so it's just going to stick in a loop and call analog read to sample input from the microphone. And then it's looking for the minimum and the maximum value from those samples. So this sample window value, if I go back up to the top, you can see it's set to 10. And if we look at the loop code here, it says it's basically going to sample for that number of milliseconds. So it's going to spin for 10 milliseconds, just constantly reading the analog input from the microphone. And during that period of time, it's also going to look and see what was the highest signal and the lowest signal that I saw. So that kind of gives you a range. You can imagine, because sound is a sine wave that just goes, up and down, just constantly up and down. And for a louder signal, it goes up and down, a really high value. Let me see if I get my finger in here. So, really high up and down, really large range. Versus if it's a small value, it's going to go just a very small up and down. And so that distance is smaller. And that's what we're looking for here. So we look at a window of time. Because we know this signal is a sine wave that's going to go up to a high value and down to a low value, we're looking for kind of what those min and max values are in this block of code. And then we figure out what's the distance between the maximum and the minimum signal. So you can imagine, let's say my signal, it went up to a high value here and down to a low value here. What is this distance in between here? So for a loud signal, it's going to be really high. There's going to be a big distance. And for a low signal, it's going to be really small. There's going to be, a very small distance in between here. And so that's what that peak-to-peak computation here is saying, is, figure out what is the amplitude or the size of that sine wave of sound that we're reading from the microphone. And that's kind of the magic trick of how you convert a microphone signal into a volume level. You can't just look at a single sample and know like, oh, this is a value of 700, so it's obviously a very loud signal. Because, the microphone, there's some bias to it, and it's really like, what if the sample right before that 700 was a value of like 690, and that was your minimum signal? Then in reality, your difference is only 10, and so that's actually a very soft signal, even though it's at a high level as far as the analog to digital converter sees. It's that changing signal, it's that length or size of that changing signal that really matters here. So that's what this block of code does. It's just figuring out for some period of time what's the amplitude of the signal that we see. And then once I have that, that's really all I need. I could just scale that directly to light up the pixels, but we can go through and see kind of how this code works. So after it figures out the size of the signal that it's seeing from the microphone, then what it does, this little block of code, it will actually light up all of the pixels to a rainbow kind of set of colors. It uses this wheel function that's in the NeoPixel library. We use it a lot. And basically this just does some really nice little math to do a nice color gradient based on a changing value. So you don't really need to understand exactly how this works. Just understand that as you give wheel a value that increases, it goes through a different set of rainbow colors, because it's actually, color math is a little tricky when you get into like hues and hue saturation value, like different color schemes and things. the math actually gets pretty complex. You can look at Wikipedia articles for it. It's actually pretty fascinating, and especially if you're into computer graphics, like look into color and color math. There is a lot of cool stuff there. But that's all that this function does. So it's not even looking at that peak-to-peak signal yet. It's just lighting up all of the pixels, just sets them all on to a rainbow kind of color signal. And then it calls this f-scale function. And basically what this does is this scales this peak-to-peak value to some value within 0 to 10 that's going to, map to my range of pixels. And this is very similar. Remember that Arduino map function that I showed last time? Let's search for this. So the map function in Arduino, super handy function. It scales from one range to another range. So if I have a range from like 0 to 10, and I have a value within there of 5, so that's halfway in between my range of 0 to 10, and I want to scale that to a range of like maybe 500 to 1,000, then this will actually, if I give it a value of 5 from 0 to 10, that's halfway in between, it's going to give me an output that's halfway in between 500 and 1,000, so it would give me like 750. And so that's a really easy way, and I showed that in the previous video, of taking a simple analog value, using map to map it to like the number of neopixels to light up. Now the interesting thing though, this function, so we're not using map because this actually does a logarithmic scale and not a linear scale. So it's using a curve, whereas a linear scale is just like a straight line, like increasing or decreasing. Whereas a logarithmic scale has like a curve to it. So you see, it might go slowly, like it's, not increasing much, and then boom, it just shoots right up to a higher value there. Or actually, I think logarithmic, maybe it falls down to a lower value. But the general idea is it's not linear. It's not just a one-to-one kind of constant increase. The slope actually changes as it goes. And you want to do that actually because sound itself, the volume that we hear, is not a linear relationship. So if I'm talking really softly, and then if I'm talking really loudly, it's not a linear increase. So, like maybe if I'm talking twice as loud, the values that we're reading wouldn't actually be twice as loud. There's actually a logarithmic increase. It's an exponential increase. It's powers of 10 basically. So decibels are typically what you hear as far as how sound is measured. And that means it's an increase in 10 times. So when I'm talking twice as loud, it's actually a 10 times increase in the signal for that. And so that's why we're using a different scaling function, one that we actually define ourselves. So if we go down to this f-scale function, and I'm not going to get into the math of this too much, but really all that this is doing is just, it's like the map function. It takes in like, what's my original scale, like the minimum and maximum values for my signal. What's the new scale that I want to map this to, like a value of 0 to 10, like the number of pixels, the range of pixels I want to light up. And then what's my input value within this original range. And then you can kind of give it a parameter to tweak the curve, like to increase the curve or decrease the curve. And this just applies some math to figure out, okay, where do I fit this new point along this curve, so that it's going to give me a value that follows this exponential curve instead of following just a linear curve like the map function would follow. And so that's why, because if I didn't do that, if I just used the map function, you would see that the volume doesn't really increase. If I talk twice as loud, it's not going to light up twice as many pixels. It would light up probably less pixels instead of that. So that's why we do this conversion and why you see it using this this function here. But really just think of it like all this function does is map from the volume level we see from the peak-to-peak values to which number of pixels that volume level would map to, from 0 to 10 pixels on here. And then once I have that value, this little bit of code right here basically turns off all the pixels that are above the volume level. And so it uses this little draw line function, which basically just says, okay, if I measure my volume level like at pixel number 4 right here, then the previous code actually lit up all of the pixels, but now this block of code says, okay, go from pixel 9 all the way down to pixel 4 right here and turn them all off. Set them to color 0. So you see right here, it sets them all to color 0. So that's all that this bit of code does, is just turn off the pixels that the volume level doesn't change. And then this little bit of code right here actually says, turn on the maximum pixel that we saw. So that's like, if I talk really loudly, you see like the pink pixel lit up right there. And that's kind of your maximum value. And so that lights up your maximum value so that you can see that. Then this strip.show, that'll actually show the pixels. And then this last little bit right here, this is actually where it does some animation where you can see that max pixel kind of falls back down to 0. So this is where it's doing that, like it waits for a little period of time to let the pixel fall down right there. But really that's all there is to this code. You know, it looks pretty complex, but it's very similar to the analog sensor kind of demos that I was showing before, you know, but this time we're just looking at a signal and not just a single analog reading. And so once we figure out that signal and we figure out the size of that signal, then we can go through and start adjusting the pixels based on the size of that. And you saw here how we used, you know, not just a linear mapping, but an exponential or logarithmic mapping to change that signal because it changes at a different rate. You know, it's not a linear signal with the sound volume there. So that's really it. That's all there is to this code. And it's, you know, anytime you're dealing with volume levels, you want to use code like this. You know, treat it like looking at the amplitude of the signal, looking at, you know, what's the pressure level as a logarithmic relationship to this sound. So that's pretty cool. Now the next thing I wanted to do, I wanted to turn this into a wearable project. So I've got a fancy little jacket right here. Let's turn this into something that I can actually wear and, you know, pin it to some clothing or something like that. So I was thinking an easy way to do this, I've got a few little bits of material. So, you know, this Circuit Playground board, I picked up these things. These are some name tag magnets. They're actually name tag holders, but I just cut the magnets out of here. So I've got a little magnet here, and these are kind of nice. They're you know, basically you'd hold a name tag on. So there's two parts. There's this part has a bunch of little neodymium magnets, and then this is just a metal backing that just sticks to it. And so this is nice if you want to attach something to clothing. You know, if I attach one half of this to Circuit Playground and then the other half I can put it on clothes, you know, and you can hold the Circuit Playground to yourself. And then the nice thing with Circuit Playground right here, so at the end right here, this is a JST connector where I can plug, you know, something like this in. This is a little LiPo battery. So real quickly, let's just put this little name tag magnet on the back of Circuit Playground, and then I should be able to wear it. And, you know, it's running the VU meter sketch right here, so, you know, you can walk around and show people, hey, look at this, you know, it changes as I talk, and pretty cool kind of little demo of it. Now to attach this, let's see, and let me change to the main kind of workbench view right here. Let's go to that, and let's turn that off. So let's do this. Yeah, there we go. And maybe I'll zoom out a little bit so that we can kind of see more of the workbench. Okay, so this is what I was thinking. So, you know, I've got the magnet. There's this half here is kind of nice and it's plastic. I think this is the half that's made to go kind of inside your clothing. And then this half right here is just metal. Now I do want to be careful, so I'm going to unplug Circuit Playground. So I'm thinking, you know, let's take Circuit Playground and let's put this metal part on the back there. And then, you know, I can attach the magnet like that on there. But I do want to be very careful because this is metal and there are pins on here, or these output connectors that could short out. And in particular, you know, this one on the left right here, this is 3.3 volts. This is ground right here. So if I short both these out, that would be bad because basically the that 3.3 volts is the output of the regulator. That's going to go straight to ground through, you know, this piece of metal that has almost no resistance at all. So that could just completely kill your regulator pretty easily. So I don't want this metal to touch Circuit Playground. So what I was thinking is I'll use this. This is just some double-sided foam tape. And it's nice in that it's got some thickness to it. So you can see it's like, I don't know, maybe like a 1/16 of an inch thick or so. And so that'll give me enough, you know, kind of clearance where I can put the tape on Circuit Playground and then put this on top of the tape. And then that should protect it from touching the Circuit Playground board and shorting out. The other way I could do this is I could put this, because this is just plastic, I could put the plastic down and that would be fine. Like I could just hot glue it onto the Circuit Playground. But I figured I would do it this way because this plastic bit's a little easier to hold, and this is the part that you're going to pull off of it when you put it on clothes, so it might be easier to put, you know, this side on here. So I'm just going to cut out a piece of this double-sided tape. So I'm just going to stick this metal part onto one half of this. I'm just going to cut around it so that we get you know, pretty rough outline of it. So get that, and then we'll cut this. All right, that's easy. And then now this half, I'm going to pull off the backing there. So there we go. That's easy. And now I will try to get this relatively straight. on the back there. So we cover that up, all right. And then give that a good press just to make sure that it's on there. So that looks good. Okay, that's cool. Now this should be, yep, look at that, it just sticks on with a magnet, so that's nice. Then I can pull this off, and you do want to be careful, like if I just yank this straight off, I could rip the tape off, so I'm just gonna kind of slide it off the side like that. So, okay, cool, that's the world's easiest wearable product. Even I can do it, I'm not a wearable expert, but hey, look, if I can do it, you can do it. Okay, so that's easy. So now let's see, let's go back to the main headshot here. Let's do that. And okay, so let's move the camera down a little bit here. So I'm sporting this nice jacket that's got, look at this fancy little pocket here. So I should be able to, if I take my Circuit Playground, and if I put it right here, all right, so it says, you know, members only, but hey, we'll cover that up, Circuit Playground only now. And let's put the magnet behind here. There we go, that sticks on, so that's cool. So I've got that. Let's see if I can center that. And then the nice thing, because I got a pocket here, I can just put my battery inside of there. So we'll throw that in. And then let's plug in the battery, and let's see. All right, check that out. So how's that working? So we got Circuit Playground, got Transistor Man, of course. So I'm all decked out in Adafruit gear here. But that's cool. That's, you know, the world's easiest wearable project right here. And you can see it's lighting up as I talk. So if I talk really loudly, it goes up a lot. And if I talk a little bit softly, it goes down kind of low. But that's pretty cool. And you can put this on anything. You know, you can put this on a jacket. You can put this on, put it on a hat maybe, put it on, you know, clothing. Very simple, fun and easy. And it's, you know, a good demo of what you can do with Circuit Playground because it's got a microphone on there already. You know, you didn't have to solder anything up. Just run the right code to read the microphone and then convert it into different color values to light up the NeoPixels and build a fun little easy wearable project with it. So I think that's it. I think this is the what I wanted to show in this stream. So let's see. Let me move this up a little higher so I can get closer to the computer here. Oops. I lost it in the pocket. There we go. It's somewhere in here. There we go. Get that out. All right. So let's see. Let's see. I can put this thing probably. Let me put it up here. That works. Let's just stick the magnet up there. Oh, come on. About to lose it again there. There we go. Almost there. Got the strap in the way. There we go. So that works. That's kind of like a almost like a corsage. That would be a cool. Hey, if you're I don't know, is it past prom time? I never remember the time of the year, but this would be, you know, do a digital corsage with Circuit Playground or something like that. That would be cool. That would get some attention. Although you got to figure out a good place to put the battery up. What you could do, you could probably make a longer cable. You know, just get some JST connectors and make a longer cable, and then figure out a way to, like, you know, get it in, maybe hide it inside of your jacket or something like that. Just tape it to the back there. But that's cool. You know, it's the world's easiest wearable project with Circuit Playground there. So let's see. I'll see if there are any questions in the chat. Feel free to throw them in there. Let's see. So, can you join a strip of NeoPixels to the onboard ones? No, good question. This one's come up a couple times. With Circuit Playground right now, no, you can't access the output signal. So basically, the NeoPixel starts right here with digital pin number 17, and then it goes all the way around the board to the end pixel, and we don't have the output signal broken out. But you can use any of the digital outputs as an input to an external strip of NeoPixels. And then, you know, you can use the NeoPixel library yourself and create another strip of pixels if you want to light them up. So just a little extra complexity. But yeah, it's not exposed, but it's you can still add external pixels to it for that. So, and I think that's it as far as questions go. Yeah, that's it. So thanks a lot for watching. Subscribe to youtube.com/Adafruit. You'll see this video and all kinds of other videos. Subscribe to twitch.tv/Adafruit, and you can watch me stream these things live. I'm starting to do 3 streams a week. I'm thinking maybe it'd be fun for at least the next few weeks to do a Circuit Playground stream every week, like do some new interesting demos with it. So I'll keep that up. Monday is kind of my Raspberry Pi. I realized a good name. I'm going to call it the Raspberry Pi Quick Looks. Kind of like, you know, video game quick look. I like to look at interesting software in the Raspberry Pi world. Like this Monday, I looked at Chromium OS, which is a version of the Chrome OS operating system for Raspberry Pi. And then Fridays I like to do more in-depth kind of, programming related stuff. So last Friday I wrapped up a 4-part series on talking to Wi-Fi boards with a Raspberry Pi. So this Friday I'm going to do probably just a 1-part series. I think I'm going to do on data storage, like how to store sensor readings, using like a basic SQLite database or like a CSV comma separated file, maybe even how to store some basic program state, stuff like that. So that's what I'm thinking of doing this week on Friday. So yeah, tune in, check out those shows, like, comment, subscribe. That lets us know that this stuff is useful and that people like it and they're getting good stuff from it. So thanks a lot. This is Tony from Adafruit. Oh, and by the way, too, also today, later today at let's see, I think is it 7:30 p.m. There's Show and Tell, and then 8 p.m. is Ask an Engineer. That's Eastern Time. Ask an Engineer. So check out the live streams. Been doing those for 6 years now, I think. So that's a lot of cool content from Adafruit for a while. So cool. Thanks a lot, and I'll see you guys later. This is Tony from Adafruit.